Hello class, welcome to Geometry Lesson 4.6. We're going to talk about congruence and overlapping triangles. And the essential question we want to address is, which theorems can be used to show that two overlapping triangles are congruent? And the goal today is to be able to use triangle congruence to solve problems involving overlapping triangles. And so this lesson is going to involve just a bunch of examples with overlapping triangles and being able to apply the theorems that we've learned in the previous lessons. So in this example, figure ABCD is a rectangle with diagonals AC and BD. Identify the corresponding sides and angles in the two right triangles indicated in the diagram. So the two triangles that we're concerned with here are the blue triangle, triangle ABC, and this red triangle, triangle DCB. All right, so what we're going to do is I'm going to take the blue triangle and I'm going to reflect it across the vertical line, this vertical line that's indicated in black. And this vertical line is the same vertical line that would cut the rectangle in half. And so if I did this, then I would have this original blue triangle reflected will look like this. And we have, and notice that the B and the C flipped because they got reflected. And so now we have a new triangle, triangle ABC, and we can compare that with the triangle DCB in the red above. So now we're going to go ahead and look at corresponding sides and angles. So we can see from the diagram that AB corresponds to DC, BC corresponds to CB, and CA corresponds to BD. You can also see from the diagram, now that I have it reflected, that angle ABC is congruent to angle DCB, and that's the right angle indicated in the diagram. We can see that angle BCA is congruent to, or is corresponding to angle CBD rather, because we're only listing the correspondings here. And angle CAB corresponds to angle BDC. And so now we know that which sides correspond to what and why. And we can see that based off of the reflection that we made. All right, example 2. We want to address the question, is angle EGD congruent to angle EFH? So we're basically looking at this angle EGD and EFH, so those two angles. All right, so in order to do this, we're going to come up with our statements and reasons just to kind of organize our thoughts here. So the first thing that we want to address, well, it's first what's given. What's given in the diagram? Well, we know that DE is congruent to HE, and that's because of the tick marks that we have here. So now that we know that information, we also know that angle D is congruent to angle H. And how do we know that? We know that by the isosceles triangle theorem. So we know that these angles are congruent. Remember, the isosceles triangle theorem states that if you have an isosceles triangle, meaning you have two opposite sides are congruent, or two sides are congruent in a triangle, well then that means that the opposite angles are congruent as well. And so this is how we determined that angle D is congruent to angle H. So now we're going to use the other piece of information that's given in the diagram. We know that DF is congruent to HG because of this tick mark here. And so now with those pieces of information, we're going to come up with another statement. We know that FG is congruent to itself, and that's because of the reflexive property of congruence. And the reason why we do that is because now we want to show that DG is congruent to HF. So now we know that if I were to take these two line segments, DF and FG, well, that's going to be the same as taking the line segments HG plus GF. And those two line segments are identical. This is called the segment addition postulate. Remember that if I take this line segment and this line segment, that's going to give me DG. And then if I take HG, which I'll call this 1 prime, just to kind of distinguish this from the 1 here. If I take this and I add it to 2, then that gives me HF. And we know that since 1 prime and 1 are the same, and 2 is identical to itself, then these two segments, these two sets of segments, they add up to the same length. And so we know that DG has to be congruent to HF. Let's put it another way. So for example, if I know that DF is 3 inches, and I know that HG, it has to be 3 inches as well because they're the same. And then I know if FG is 2 inches, well, 2 inches is equal to 2 inches. It's equal to itself. And I know that 3 plus 2 is 5. And I know that 2 plus 3 is 5. And so they add up on both sides to the same length, which is how we said that DG is congruent to HF. All right, so now that we established that by the segment addition postulate, those two segments are congruent, we can go ahead and establish that those two triangles are congruent. We can establish that DEG is congruent to HEF. Why is that? Well, because now we know that by SAS, we know that DE is congruent to HE, so that's a side and a side. And we know that the angles here, angle D and angle H, are congruent, so that's an angle. And now we just established that DG, which is a side, is congruent to HF, which is another side. And so we established that we have a side angle and a side for both triangles, and therefore we know that these two triangles have to be congruent. All right, so now we established that those two sets of triangles are congruent. And let me go ahead and outline the other one in another color here. So we have this purple triangle that's congruent to this red triangle. All right, so that's by SAS. And so now that we know that those two triangles are congruent, then that means I know that angle EGD, which is this angle right here, has to be congruent to angle EFH. Why is that? Because these two triangles are congruent, which means that those two angles have to be congruent based off of corresponding angles, corresponding sides and angles. And this is by the CPCTC. The corresponding parts of congruent triangles are congruent. And we should probably indicate this with a double arc because we already have a single arc for these two. So we know angle D is congruent to angle H, single arc. And so angle EF is, this angle here is congruent to this purple angle, double arc. All right, so we showed that those two angles are congruent. Now let's look at another example. So show that BFE is congruent to CEF. So BFE, so we're referring to this triangle, is congruent to CEF. All right, so let's go ahead and combine our thoughts. So the first statement that we know that is given in the diagram is that AF is congruent to DE. Now we're going to use the reflexive property of congruence and saying that, well, FE is congruent to itself, right? And so it's congruent to itself by the reflexive property of congruence. And now, similarly to before, we know that AE is congruent to FD or DF because AF plus FE is going to give us AE, and that's the same thing as FE plus ED, which is going to give us DF. And we know that those two things are the same because we know that FE is congruent to FE, and we know that AF is congruent to ED based off of this statement, based off of what's given. All right, so now we have AB is congruent to DC, and angle B is congruent to angle D, and that's just given in the diagram here. Now we're going to establish that the two triangles ABE and DCF are congruent by side, angle, and side. So this purple triangle is now congruent to this red triangle. Now that we established the side, angle, side for each of those triangles. So now, because we know that those two triangles are congruent, we also know that BE is congruent to CF. So if we look at this, we know that this BE is congruent to CF. And we'll use another set of tick marks here. 1, 2, 3, 4. We know that those two have to be congruent. Because why are they congruent? Well, they're congruent because those two triangles are congruent, which means that those two corresponding sides are congruent, and that's by the congruent parts of congruent triangles are congruent. So that's the CPCTC. We also know that angle CFD, CFD is this angle, is congruent to BEA, which is this angle. And similarly, that's because, you know, and I'll use this to kind of demonstrate another color here too. So this angle corresponds to this purple triangle, and this red triangle corresponds to this red triangle. Or this red angle is for the red triangle. And we know that those two angles are congruent because they correspond to each other for the congruent triangles. And let me do this in purple to kind of demonstrate that. All right, so by the CPCTC, we know that those are congruent. And so now we know by side, angle, side for the purple triangle, as well as the side, angle, side for the red triangle. Now we know that those two triangles have to be congruent based off of SAS. And so now we're looking at these triangles in the middle. And I'll go ahead and eliminate the rest of this information just to kind of show you. So now we know that those two triangles in the middle are congruent by SAS. Or by the CPCTC, but which means that the two triangles are congruent by SAS. All right, so we proved that BEF, triangle BEF is congruent to CFE. So let's look at another example. Draw separate diagrams showing triangle AEC and triangle DBG. So this is a little bit different. This is just showing, basically taking apart the two triangles, taking apart the diagram and reconstructing the two triangles based off of the diagram. So if we look at triangle AEC, that's given on the right, and let's reconstruct. DBG in purple. And so now they're exactly the same. I just translated them. And so now we can see that based off of the diagram, GD corresponds to AC, and that's because of the segment addition postulate. Because these two segments, by the segment addition postulate, is congruent to these two segments by the segment addition postulate, which I'll say, I'll abbreviate it as SAP. And by the diagram, angle C is congruent to angle G. So this angle C here is congruent to this angle G, which is BGD. And then the angle B is congruent to angle E in these separate triangles based off of the diagram here. All right, so that's the information that we know. That's all we know based off of with the diagram. And so you can see that these two triangles are congruent. Triangle AEC is congruent to triangle DBG by the AAS, because we know we have an angle, angle, side, angle, angle, side. All right, so example 5, name a theorem that can be used to prove that each pair of triangles is congruent. So for the first part, part A, we want to show that triangle KLM is congruent to triangle MJK. So what theorem can be used for this? Well, if you look at this first triangle right here, we know that we have a side, and these two angles, or these two sides, these two two sets of 3 tick marks add up to another side, right? And in the diagram, it should say, and I forgot to mention this in the diagram here. The diagram should say that these are identical as well. So there's a little mistake on that diagram, but now we included it here. So that's another side. And if you look at this other triangle, this other half, we have a side corresponding to the other side, this side corresponding to this top right side, and we have this side is congruent to itself, which, by the reflexive, well, this side is congruent. It's the same length side, so basically it's congruent to itself by the reflexive property. And therefore, we can say that this is SSS. So we can prove that these triangles are congruent by SSS. Now for the second diagram, we have an angle corresponding to this angle. And we know that this angle is the same angle for this triangle as it is for this triangle. And that's by the reflexive property as well. That angle is congruent to itself. And then we know that based off of this diagram, that this side is congruent. So this is another side, and that's congruent to this side. And so what we have is, what looks like is we have an angle here, and a side. And we have an angle here, and a side. So this is AAS. So this is by the AAS congruence theorem. Now for the third one, we have a right triangle here. And we're looking at this right triangle. And notice that we have a hypotenuse, we have a leg, and so we can probably use some kind of hypotenuse leg theorem. Now if you look at this other right triangle, it's a right triangle. We have a hypotenuse corresponding to a hypotenuse on the other triangle. We have the same leg corresponding to the same leg on the other triangle. And so this is definitely going to be an HL theorem. Alright guys, that's going to do it for the video. I hope you found this useful. And as usual, I'll see you in the next one.